Welcome back to the Explainer. Today, we're diving into something absolutely wild. We're setting off on a journey to fix a 400-year-old mathematical fracture. Literally, a hidden structural flaw in abstract geometry that is draining massive amounts of computing power every single day. So think about this for a second. What if the fundamental math powering our modern computers is actually broken right down at the structural level? We're going to explore the massive, real-world stakes of exactly how we model physical space in scale. To really grasp the problem here, we have to introduce our main antagonist for this explainer. It's known as the trig wall. And to find its origins, we actually have to go all the way back to 1614, to John Napier's discovery of logarithms. You see, Napier established this continuous point-line paradigm. Now, don't get me wrong, it was completely revolutionary at the time, but it essentially resulted in a one-dimensional topological collapse. In modern computing, this legacy continuous system forces our chips to calculate transcendental functions, things like sine and cosine, using infinite decimal approximations. It's kind of like trying to build a perfectly smooth circle using square Lego bricks, you know? The system just lacks a physical surface to hold the information, so computers are forced to struggle against endless decimals, wasting immense amounts of energy in the process. To deconstruct this, here is our roadmap. First, we'll look at hitting the trig wall, then lay a new geometric foundation, slice the Cartesian plane, explore Sporner doubling to 16, build the octagonal lattice, and finally arrive at bit-perfect computation. Okay, let's jump right into sections 1 and 2, hitting the trig wall and building a new geometric foundation. We are really contrasting two entirely different paradigms here. The old continuous system relies on these invisible, infinitesimal points mapped out on a ghost grid. Base-scale calculus, on the other hand, uses a discrete mereological foundation. Now, mereological just means it's built on the strict relationship between physical parts and wholes. So instead of invisible points, it uses tangible, puzzle-like triangular surface regions, we call them tiles, as the actual primary primitives to hold information. So how exactly do we build this new foundation? Well, first off, instead of the Euclidean standard of fixing some arbitrary radius, this system anchors right to the side A transverse constant, where A equals exactly 1. This totally shifts our coordinates into a reciprocal integer domain. We basically throw out the abstract infinitesimal origin point of 0 and replace it with a physical surface called a quark. By doing this, it creates a metabolic ground. That means the computer never has to guess where it is in space. It's always anchored in perfect, stable integers. Moving right along to section 3, slicing the Cartesian plane. Let's play the role of visual architects for a minute and physically modify that standard XY graph we all grew up with. All right, here is the actual mechanical build. We start with the 4 physical Cartesian axes. Then we have them using a pi/4 symmetry, which is based on an isosceles right triangle. This specific 3-piece set logic partitions the continuous space into discrete, manageable rational shards, perfectly establishing the diagonal square root of 2 over 2 diamond axes. And here's the massive payoff of establishing those diamond axes. It introduces what's known as the difference of squares engine. Because of how we've systematically partitioned the space with these physical tiles, navigating this geometry no longer requires complex, power-hungry trigonometry. Instead, geometric rotation is transformed from a battery-draining calculation right into a native, low-power algebraic bit shift operation. It's a total game changer. Now, for section 4, spin or doubling to 16, where we drastically expand our geometric state space. As the spiral pattern completes a full 720-degree rotation in what's called the second loop, we apply spin or doubling to those axes we just built. We essentially track 2 separate geometric features simultaneously. The line Z sequences track the physical boundary edges, while the point Z sequences track the vertex corners, or, the pointiness coordinates. By forensically tracking these boundary edges versus the vertex corners, we perfectly double our geometric awareness from 8 right up to 16. And through that exact spin or doubling logic, those edge and corner sequences map flawlessly into a symmetric diamond tile spiral. We have officially established 16 discrete bit-perfect spoke phases. What we're looking at here is a formalized 4-bit state machine. It navigates 16 angular positions through simple bit shifts, completely bypassing that continuous trig wall we talked about earlier, ensuring absolute structural stability. Section 5, the octagonal lattice. Let's see what kind of shape naturally emerges when we lock these 16 spoke faces together. When you interleave those point Z corner sequences and the line Z edge sequences together, it is a thing of beauty. They perfectly align to form the 8 primary vertices and 8 primary edges of a rational octagon. This specific mapping establishes the octagonal scaling horizon. By replacing the fuzzy, totally uncomputable circular approximations of legacy polar models with this discrete octagonal boundary, the math literally gets trapped in a bit-perfect frame. It stabilizes the metabolic flux right at its physical geometric limits. Basically, the math is now completely secured against the cumulative errors, endless rounding, and agentic drift that absolutely plagues standard continuous math. Finally, Section 6, bit-perfect computation. Let's bring all this dense, beautiful geometry back down to the real-world engineering pitch. 0.05 picojoules. Let that sink in. That is the microscopic metabolic energy floor achieved per operation. It is a mere fraction of what our current chips burn. Because the counting maps to these discrete, bit-perfect clicks rather than struggling with infinite decimal approximations, base-scale calculus achieves an astonishing level of low-power efficiency. Which leaves us with this final, truly provocative thought. If the universe fundamentally calculates using discrete mereological tiles rather than the continuous curves we've just assumed were true for 400 years, what other impossible computational walls can we bypass next? This isn't just a clever new way to do math. It's a completely new way to read the fundamental building blocks of physical reality. Thank you so much for joining me on this explainer, and I'll see you next time.